In this lecture, I want to talk about the chain rule, which is a method for finding the derivative of a function that is a composition of two functions. So something like this, where the big F is a function of x, where f is a function of g of x. So, for example, we could have something like cosine of x squared, or x squared plus 9 to the fourth, or maybe e to the x squared. These are all examples of compositions of functions. So you have, like, the outside function here would be cosine, and the inside function is x squared. The outside function here would be x to the fourth. The inside function would be x squared plus 9. And in this case, it's e to the x squared, so the outside function is e to the x, and the x squared replaces the x in the definition of e to the x. So these are examples of compositions, and what the chain rule states, I'll just give the statement first and then give an example that maybe helps us to make sense of what the chain rule means. So we take the derivative of the outside function evaluated at the inside function times the derivative of the inside function. All right. So so you can see we have two rates of change going on here. We have the rate of change of f at g of x times the rate of change of g of x. So I wanted to just give a kind of a real life type of example, and you can think about if you've ever been to the airport and you see these walkways, these moving walkways that you can walk on so that you can get faster. If you're late for your flight, you want to be able to get to the gate quicker. When you're walking on one of these walkways, there's basically two things going on, and this is how we can think of a composition of functions. We have, maybe you could think of the outside function as being the walkway and the rate at which the walkway is moving. So we might say that the walkway, this moving walkway, is moving at a rate of, let's say, 4 feet per second. All right. But then you would have this, while you're on the walkway, kind of the inside function is the walking. You're actually walking, right? So you might be walking, so that's changing at the same time. And let's say, I don't know, I'm thinking maybe like 2 strides per second, or about 6 feet per second seems reasonable. All right, so if the walkway is moving at 4 feet per second, and you are on the walkway moving at 6 feet per second, hopefully it makes sense that 4 times 6, you're moving, your position is changing at a rate of 24 feet per second. So if we think about this in terms of the chain rule, we can think about kind of the derivative, or the rate of change of your position with respect to time, right? And then you can think about that as the rate of change of your position with respect to the walkway. So that's how fast you're walking, right? This is how your position is changing on the walkway times the rate of change of the walkway with respect to time. All right, so these actually kind of flip this around, because we said that this walking that you're doing on the walkway, we said that was 6 feet per second, and the walkway is moving with respect to time at 4 feet per second, so you still get this 24 feet per second. And so you can see this is kind of like this piece right here, and then this is like this piece. But the point is, you have rates of change being multiplied. That's the big idea here, and that's why this makes sense. When you have two things going on in this composition, like walking on a moving walkway, then the rate of change of that whole thing is going to depend on the rates of change of each of the individual ones. That's basically what the chain rule is saying. And then this also, with this, there's another kind of way of thinking of this, notationally that I think some students find helpful. So one way to think of it is, if you have this f of g of x, then we might let u equal g of x. We're just going to call it u. And the reason is then you basically end up with something, your function is y equals f of u. So if I wanted to find y prime, then it would be f prime of u times g prime of x. And in terms of the Leibniz notation, we could think of this as the change in f with respect to u times the change in u with respect to x. And although technically these aren't fractions, you can kind of see this du term. This would give you df dx. So again, we have this multiplication of the rates of change. And these, like I said, these don't really cancel, but you can see kind of your df dx in here in terms of this rate of change times this rate of change. And this is another way to think of, how you could execute this procedure. So what I would like to do is go through each of these examples using the chain rule so we can kind of see how it works. So, so the first one was cosine of x squared. And at least for this first one, I'll do it both ways. So if we think of f of g of x, we have an outside function and an inside function. So f of x is cosine x, and g of x is x squared. So f prime is negative sine, and f prime of g of x is negative sine of x squared. And then g prime, of course, is just 2x. So f prime of g of x times g prime of x is negative sine of x squared times 2x, which we might write as negative 2x sine of x squared. Alternatively, we could have let u equal x squared, right? That's the inside, so when we talked about doing it this way here, we could let u equal whatever the inside function is, and let f of u be cosine of u. All right, and then we said that df dx is df du times du dx. Well, df du is negative sine u, and du dx is 2x. So now, in order to get everything back in terms of x, we just substitute, right? So negative sine, we know that u equals x squared, so we can just put our x squared back in, times 2x. Of course, we can rearrange that. We get the same answer that we did before. So I just wanted to show both of these notations because I think sometimes thinking of the inside function as something like u makes it a little bit easier because now we're just doing cosine u. We don't have, it seems more like two separate functions rather than a function of a function. Okay, so there's that example. Let's go back to, what was the other? There's a couple more that we wanted to look at. All right, so we had something like x squared plus 9 to the 4th. All right, so I don't know, let's say f of x is x to the 4th, g of x is x squared plus 9. So f prime of x, of course, is just 4x cubed, and f prime of g of x is 4, and now I'm going to put in g of x for x here, and that's this, so it's 4 times x squared plus 9 cubed. And then g prime is just going to be 2x. All right, so finally the chain rule, you have f prime of g of x times g prime of x. So I just have to multiply this with this. If I multiply the 2x times the 4, I actually get 8x times x squared plus 9 cubed. All right, so that's how we would find the derivative of something like this. What I would like to do here, though, is to generalize. Because anytime we have something to a power, you see that we basically kind of have, we have the power rule in here. It's just that we'll have to multiply on by the derivative of the inside function at the end. So if I had just any function, you know, let's say g of x, and it was to the nth power, and I wanted to take the derivative of that, then using this outside, the outside function would be x to the n, right? So the derivative would just be n to the n minus 1, right? That's basically what we did here. And then the inside function just stays the same. So even though we don't know what it is, we can just call it g of x. And then we would multiply by the derivative of whatever that inside function is. So in general, when you have some function to a power, you can use this, it's called the generalized power rule, because it works for any function here. Notice that this would actually work, sorry, I guess I'll finish what I just said here, the generalized power rule. Notice that this is a special case of something like x to the, I don't know, 5th, because I would have, right, so you could think of the inside function here as being x. So let our inside function be x, it's g of x, right? So then the generalized power rule says this will be 5 x to the 4th times g prime, well, but that's just going to be 1. So this is 5x to the 4th. And this is what we mean by generalized. This, the power rule, then becomes just a specific case of this more general rule that works for any function g prime. It's just that in this special case, when g of x is x, then we're multiplying by 1, so we just have the 5x to the 4th. Okay, last example then. Let's take a look at e to the x squared. Let's say I want to take the derivative of that. So again, let's let, we'll use the other notation this time. We'll let u equal x squared. So that's our inside function. So our f of u is just e to the u. So then df dx is df du times du dx. Well, df du, well, the derivative of e with respect to u is just e to the u times, and then du dx, we've already done this one with the other example, that's just 2x. And then finally we want everything to go back to x. We know that u equals x squared, so this is e to the x squared times 2x. Or, if you want to put the 2x first, 2x e to the x squared. Okay, so this is another case that's a specific case of a general rule. So let's think of taking the derivative of e to some function of x. All right. Now notice, because if we let u equal f of x, then I'm going to end up with e to the u, right? And then I'll always end up, when I take the derivative of this, right? If we're calling this, well, poor choice to call that f. I could call it g, but the point is the derivative of this is still going to be, when I take the, let's use the prime notation, I'm just going to end up with e to the u. So this part right here, notice I started off with e to the x squared. Because the derivative of e to anything is just e to the same thing, I'll always end up with this e to the same function that I started with. The difference is I will have to also then multiply by, so if I want to take this, if I'm going to do the df du, so df du will still be e to the u, and then I'm going to have this du dx, and that's going to be f prime. All right? So, because that's what u is. So I'll always get back this e to whatever I started with, in this case e to the x squared. You see this e to the x squared show up again. But it will always multiply by the derivative of whatever this function up here is. All right? So again, we wanted to get this all back in terms of x, so this would actually be e to the f of x times f prime of x. You'll commonly see it with the f prime out front, e to the f of x. So again, this is a special case, this is the general case of what we already know. We say the derivative of e to the x is e to the x. But notice that if we use this general form here, that we get the same thing, because in this case my f is just x, and the derivative of x is 1. So I'm just left with e to the x. But just to summarize here, because this is kind of a mess, if we take the derivative with respect to x of e to the f of x, then it's f prime of x e to the f of x. And this is just a result of the chain rule, but it's a handy rule because we don't have to constantly be thinking about the outside and the inside function. This works when you have e to some function, e to the u or e to whatever. That's always going to be your outside function. The inside function is whatever the exponent is. So we always end up with something of this form.